So the last few classes, we've been working on probability distributions. Now today and also our next section, we're going to be focusing on specific types of distributions. So today we're going to look at what's known as the binomial distribution. In order for us to look specifically at the binomial distribution, we have to start off first of all with characterizing a binomial experiment. A binomial experiment satisfies the following conditions. If even one of the following are not met, it cannot be considered binomial. So it's not like, if a few of these are hit, it's okay. If even one is not met, it's no longer binomial. The first ones, there must be a fixed number of trials. So that means if you're flipping a coin, you're rolling a die, you're drawing a card from a deck of cards, it can only happen so many times. So I'm going to flip the coin 10 times. I'm going to roll the die 50 times. You're going to do it a specific amount of times. Second condition that must be met, each trial can only have two outcomes, or outcomes that we can narrow down to just two outcomes. So put them into two different categories or groups, if you will. The outcomes then are either considered a success or a failure. Those are only two options. The third outcome, the outcomes of each trial must be independent of each other. And then the fourth condition goes hand in hand with that idea of independence. The probability of success must remain the same for each trial. So the fact that the first trial happens does not affect the probability of the second trial or third trial, however many there happen to be. So each trial has no effect, the outcome of each trial has no effect on any of the other trials at all. Now, if we take the outcomes, if we have a binomial experiment, we take the outcomes of the binomial experiment and their corresponding probabilities, and we create what's known as a binomial distribution. So we've created probability distributions. Now this one is a very specific type. So for our binomial experiment, everything has to be satisfied. We know we have a binomial experiment we're dealing with, and then we're using the corresponding probabilities of the outcomes of that experiment. Now, because we are short on time today, I might not have time for everybody to get everything written down. So this information is in the green box on page 276. The binomial experiment definition. Green box on page 277. So if I flip ahead, I'm going to keep jotting those things down for you guys. So if I flip ahead, you know exactly where to go to finish the definitions. Okay, so don't, wait for me. We are short today, so I don't have that luxury today to wait for everybody. So let's look at a specific example. We have a coin being tossed 4 times. Find the probability of getting exactly 2 heads. So now the difference is I'm tossing 1 coin 4 times. I'm not tossing 4 coins. We've been able to find the probability for that of just tossing 4 coins. But for coins tossed 4 times, we want to, right now our method for doing that would be to solve by using a sample space. That's what we'd have to do at this point. Other option, what we could think about is, could this be considered a binomial experiment? So let's think about our checklist. Condition number 1. Is there a fixed number of trials? Yeah, there's 4. We're going to flip this coin 4 times. So fixed number of trials, check. Condition number 2. Are there only 2 outcomes for each trial? Yes. There's heads or there's tails. Now, if you're jotting these down, that's great. Try to abbreviate some things. You already know the actual conditions. So number 1, you don't need to write out, there are a fixed number of trials. Abbreviate it. Fixed number of trials. Or you could just simply put 4 trials. That's a fixed number. So kind of start getting in that habit of abbreviating things. I always wait in class. I know today's a little short, so I don't have that much wait time. You get to college, professors don't wait, they go. So if you can shortcut things, kind of shorthand them, I would. The outcomes are independent. So when I flip that coin the first time, whatever it lands, heads or tails, that in no way, shape, or form affects the outcome of the next toss or the next one or the next one. So they are independent. And then again, goes hand in hand. Since they're independent, that means the probability of success, in this case, which is heads, is going to stay the same for each trial. It's always going to be 1/2. So since we want exactly 2 heads, we're going to look just at the specific probability of that happening. So we'd have the probability of heads times the probability of heads, and then our other 2 we want to be tails. So it'd be the probability of tails times the probability of tails. I'm multiplying all those things together because I have 4 tosses. They're happening in a sequence. And I want all 4 of those outcomes. I don't want a head or a head or a tail or a tail. I want all 4 of those things. Now we have to consider that the 2 heads could occur on the first toss and second toss, first toss and third toss. So we have to figure out how many different combinations we have where those 2 heads could show up. We're not arranging these. So if we flip-flop 2 different heads, it's going to be the same arrangement. So we're looking at how many combinations we have of 4 things taken 2 at a time. So our notation for that, and what you guys are used to, I wrote out the entire formula. You guys are used to just doing the 4C2 in your calculator. It's the number of combinations. In this case, we're having 4 tosses, and we want 2 of them to be heads. So we have a 4C2. So then to get our actual probability, we're going to take our number of combinations, which would be 6, times the probability we had earlier that 2 of the 4 tosses will be heads. So it's not going to be enough that I just figure out, well, if 2 of them can be heads, we have to take into consideration where they occur. So first toss, second toss, first toss, third toss. So we do have to consider the number of combinations. So I know this idea is new for us, but it's taking 2 ideas that we have used. We've found probabilities before, and we've also found the number of combinations. So we're putting those 2 things together. Now again, this works when the conditions of the binomial experiment have been met. If one of those 4 is not met, this isn't how we're going to find the probability. There are other distributions that we will learn about, but for right now, this one's going to be our main focus. Now, the notation. Here is our actual formula, right here. And I do want to make just a little slight modification here for you. Instead of using all the factorial notation, everything for the combination rule, I just changed it over here to just be the NCR that you're used to. It's the same thing. All the symbols and things, again, I apologize that we are a little short on time, but these are things that I know you guys are able to jot down yourself. They can be found, and get down as much as you can now, that's fine. There's a blue box on page 277 that contains all of that same information. So if you don't quite get everything finished right now as we're talking about, that's okay. It's okay, it's on page 277. Or if you want to fill it in later, totally up to you. the one piece of this I do want to draw your attention to, the P of S is the probability of success. That's how we would symbolize it. When it comes to the formula, the variable that represents that is going to be a lowercase p. Probability of failure, the symbol for that is P of F, capital P, capital F. But when it comes to the formula, it's going to be a little lowercase q. Probability of success plus the probability of failure, if you add those together, they need to equal 1 because those are my only two options. Remember, all the probabilities, if we add them together, all the probabilities in our sample space added together need to equal 1. So I only have two options, success or failure. So when I add those probabilities together, they need to equal 1. If they don't, you're missing something somewhere along the way. Lowercase n is our number of trials, and capital X is the number of successes in however many trials that you're doing. Your capital X is greater than or equal to 0. It's less than or equal to n, which means your number of trials. So X cannot be negative, and it cannot be greater than your number of trials. Capital X, again, is your number of successes. It has to be a whole number. Whoops, sorry guys. It has to be a whole number. I can't have 1.5 successes or 2 1/3 successes. I can't do that. Again, if you didn't get quite finished, page 277, the blue box. So let's try this out. 90% of graduates of State University who apply to a particular medical school are admitted. This year, 6 graduates from State University have applied for admission to medical school. Find the probability that only 4 will get in. Now, I realize that we're in the section pertaining to the binomial distribution. I know we just looked at the formula. And so I know right away some of you are like, oh, okay, so what can I put into that formula? What's the N or what's the P? What's the Q? But let's make sure we go through that checklist of why this is a binomial experiment, why we get to use the formula, why it's a binomial distribution. So if we take a look, the first condition that has to be met is that we have a fixed number of trials. How many trials do we have? We have 6. The student applying is considered a trial. So there's a fixed number of trials. Condition 1 met. Condition 2 says we can only have 2 possible outcomes. How many outcomes do we have? 2. Either they get in or they don't. There's no gray area. We're not talking about a waiting list. It's either they're in or they're not. Number 3 said all the trials have to be independent. So does one graduate getting in or not getting in affect any of the others? No, it doesn't change. The last condition is the probability of success is the same for every trial. And again, 90% is going to be that way for person 1, person 2, person 3. It's not going to change. So all 4 conditions are met. That's how I know that I can go ahead and dig in and start finding N and X and P and Q. Now whenever I have a formula, you guys are going to find this out. I'll do this all the time this year. I like to make a list of all the variables from that formula, and then I like to label what value is going to go in for each one of those. I don't like to just try to pull things from the question and put it right into the formula. That's not me. That's how I make mistakes. When I make my list off to the side and then I input into the formula, I make so many fewer mistakes. It helps me. Take it or leave it, just a suggestion. Our lowercase n's are a number of trials. In this case, a trial is applying for admission, and there are 6 students going to do that. Capital X. Capital X is how many successes we want. A success in this case is getting in. How many do we want to get in? Is 4. Lowercase p is the probability of success. So the probability of getting in is 90%. Which means the probability of failure, which would be not getting in, is 10%. Remember, P plus Q has to equal 1 because there's only 2 possible outcomes. So the probabilities together have to equal 1. Now we can go ahead, we can do a little plugging and chugging. Probability of 4 accepted. We have 6 trials, or 6 applicants in this case. We're going to choose 4 of them to get in. The probability they get in is 90%. We want 4 of those. Probability that they don't get in is 10%. And we want 2 of those. So the exponent on the probabilities is just pertaining to how many of that outcome you want. How many I want. Do a little plugging and chugging in the calculator, and again, just for time's sake. Now this would be, I'm giving you everything, you're going to see why in just a minute. I plug and chug in my calculator, that's what I come up with. There's 2 other ways for you to get this besides directly inputting into the formula yourself and directly putting that into your calculator. There is a table in the back of your textbook on page 774. On page 774, you'll have table B. In order to use table B, you still need N, X, and P. You actually don't need Q for this table. And you will find on the left-hand side, you'll find your N. In this case, our N was 6. And then your X is the next column. Our X was 4. So we go down to 4. And then we follow the row for 4 until we meet where the 0.9 is, that column up at the top. So it should be, hang on here guys, forgot I can't ink on here. Screen sketch, there we go, perfect. All right. All right, so we go to 6, X is 4, P is 0.9, so I follow that column down, I follow this row across, and we get 0.098. So you can use the table, that's fine. The table, however, is limited to these values of P. The table is limited, but it's definitely a nice shortcut. This is on page 774. Your other option is the calculator. The calculator steps are on page 286. If you want to know where kind of the step-by-step is, that's actually written out for you. But I just want to go ahead and walk you through it. On page 286, we go second, and then the VARS key. The VARS key is highlighted in red on my screen. So second, and then the VARS key. The abbreviation above the VARS key stands for distribution. We want capital A as the option. To get there quickly, you can hit alpha and then math, because the A is up above math. If you have a newer calculator, this is what your screen will show. If you have an older one, sit tight, and I'm going to show you in just a second what you need to make your screen look like. So if you have one of the newer ones, the number of trials is your N. P is your probability of success. Your X value is how many successes you want. Now, if you have an older calculator, you need to put on your screen exactly what I have on mine. You need a 6, which is your total number of trials. Then you need your 90%, your probability of success. And then lastly is how many successes you want, which in this case is 4. So this is NP capital X. N, comma, P, comma, capital X. And again, this is on page 286 if it's something you want to try as you're doing your practice questions. This is absolutely fair game on the test for you to use. And there we see the 0.098415. Either way works, whatever you'd like to use. So now let's step things up just a notch. Shipment of 100 tires. 20 are defective. 5 tires selected at random, and each tire is replaced before the next tire is selected. What's the probability of getting at most 1 defective tire? Let's go through our checklist. Are there a fixed number of trials? Yeah, we're going to pick 5 tires. Are there only 2 possible outcomes? Yes. It's either a defective or it's not. The third one, are the trials independent? Yeah. The first draw of the tire doesn't affect my second draw, third draw, whatever the case may be. Last but not least, probability of success being the same for each draw? Yes. The reason why conditions 3 and 4 are met is because of the piece I underlined. If I don't replace that tire, my trials are no longer independent, and my probability of success changes for each trial. If I don't put that tire back, that changes everything for my next trial and the one after that and the one after that. So replacement is key in order for this to be considered a binomial experiment. So let's jot down the pieces we need. Number of trials. 5. Sorry, guys. Number of trials is 5. The number of successes that I want. This one isn't as cut and dried. It says I want at most 1. So 0 or 1. At most 1 means the most I want is 1. So that could be 0 or 1. So I'm just going to do a 0, comma 1. Probability of success. Now with this question, we have to stop ourselves a little bit here. I'm looking for the tires to be defective. I know in the real world, a defective tire is not considered a success for a company. But for our world of probability, if the event we're looking for is a defective tire, that links to the probability of success. So the probability of success is the probability I get a defective tire. So we have to be careful when we think success and failure. It's not necessarily how it applies to real world terms, it's how it applies to the event we're looking for. So the probability we get a defective tire is 20 out of 100, which you could do it as a fraction of a fifth, or I always think the decimals are easiest to work with. Let me caution you though, you can only use the exact decimals. You can't round the probabilities. It will throw off your entire final probability. You cannot round your probability of success or failure. If you need to leave it as a fraction, you leave it as a fraction. So if success is 20%, that means failure is 80%. Since I need 0 defective or 1 defective, we need to find the probability of 0 defective, and then are we going to add it or multiply it? I want 0 or 1. What's the keyword or tell us that we're going to add? I want one or the other. I don't want both. So we have to find those individual probabilities and then add them together. So for the probability of 0 defective, I have 5 total trials. I choose 0 successes. I'm not putting 100 there. This is not, I have 100 tires, I'm going to choose 5 of them. This is how many successes. How many trials do I have? How many successes do I want? So I have 5 total trials. I want 0 successes. Probability of success is 20%. I don't want any of those. Probability of failure is 80%. And I want all 5 of those. Probability of 1 defective. 5 total trials. I'm going to choose one of them to be a success. 20% success, I want one of those. 80% failure, I only want now 4 of those. Take your pick, or actually let me show you with the calculator how you can do these. These are considered cumulative because I want 0 and I want 1. What you can do, let me show you on the calculator. If you go back to our distribute menu, second vars, and we want option B. So you can hit your alpha key and then the apps key, or you can just arrow down till you get to option B, which will say binom CDF now. The C part means we're going to do cumulative. So it's going to go 0 up through wherever you tell it to stop. Our number of trials in this case is 5. Probability of success was 20%. Now the X value you enter in, and again, older calculators, sit tight, it's going to be up on the screen in just a second. The X value you put in is where you want the calculator to stop. It will add up all the probabilities 0 through wherever you tell it to stop. So if I put a 4 there, it'll go probability of 0 defective, plus 2 defective, or plus 1 defective, plus 2 defective, plus 3 defective, plus 4 defective. So I just want 0 and 1, so I'm going to put a 1. I'll hit paste. So those of you with the older calculators, this is what you would need to enter in. Your N, your P, and then the X value you put in is where you want it to stop. So we're not going to put 0 and 1 in there. You're just going to put the last one that you want. It will do everything before it. So if I put a 2 in there, I'll get 0, 1, and 2. It's where you want it to stop. So if we hit enter, 0.73728. I also wanted to make sure that I did an example today with that idea of at least 1. That was probably the most popular question for me with the probability section that we did. Probability of at least 1 means that I want the probability of 1, or 2, or 3, or 4, or 5. Now, we could set that up this way. Do 0 plus 1 plus 2 plus 3, or excuse me, do 1 plus 2 plus 3 plus 4 plus 5. That's going to take a lot of work. So instead of adding all those probabilities together, the only thing that's not accounted for is 0 defective. So instead of having to find the probability of 1 defective and then adding it to 2 defectives and then 3 and then 4 and then 5, let's do 1 minus the probability of 0 defectives. That's the only outcome in the sample space that isn't accounted for, is if I don't get any defectives. N, X, P and Q. Number of trials, still 5. X, I want 0. P and Q, we really don't have to pick out again. They're going to be the same. And we actually already found 0 defective earlier. If you used the table earlier, I'm going to jot these down for you, what the table values were. And so we'll just use that one. So again, with the at least ones, do 1 minus the probability of none, or 0. You can, if you want to, like we did up above, we had to do the probability of 0 plus the probability of 1. We didn't have any other choice. But instead of doing all that adding for the at least ones, do 1 minus the probability of 0. Make your life a lot easier. Now I know we're really starting to run short on time here, guys. I want you to go ahead. Here's the easiest formulas. Easiest formulas we probably learned all year. Mean, variance, and standard deviation for the binomial distribution. These are on page 281. There's a blue box. Whoops. Page 281, there is a blue box there with those in it. All the variables stay the same. N's your number of trials. P's probability of success. Q's probability of failure. We have mu and sigma squared. Those haven't changed. Just one quick example of that. We don't have time for both. When you look at your information, you pick out your N, your P, and your Q. Our dies rolled 600 times. We're looking for the number of ones that show. Probability I get a 1 is a 6th. Probability I don't get a 1 is 5/6. N times P times Q. Or N times P, excuse me, for mu, for the mean. Standard deviation, N times P times Q. Or variance is N times P times Q. Standard deviation is just the square root of that. If you want to try out that last example on your own, I'll jot the answers down here for you. Tomorrow I'll put the assignment and things up for you. Tomorrow will be a work day for you. So make sure, guys, you finish up any notes that you need to. Go back to any of those blue boxes or green boxes on the pages I mentioned. If you want the assignment for today, you can. I know I said give it to you tomorrow, but if you want it for today, I'll put it back up again tomorrow for you. And also the calculator is on page 286 if you didn't get to jot that down earlier.